Okay, so this is an overview of operational amplifiers. We're talking about ideal operational amplifiers, and I'll explain the ideal portion later. The other thing to know about operational amplifiers is they are often abbreviated as op-amps. So if you hear me use the term op-amps, this is what I'm referring to. An operational amplifier is an integrated circuit, or an IC. What that means is it's basically made out of transistors. So a lot of them will be made from a combination of diodes and transistors, a lot of times MOSFETs. So diodes and transistors, specifically MOSFETs. Okay. First thing to start with is the symbol for an op-amp. Looks like a big triangle with a bunch of wires coming out of it. So there's two input terminals. One is the non-inverting terminal, which is usually denoted with a plus. And the second one is the inverting terminal, which is usually denoted with a negative sign. Okay. We usually have a signal current return. This is how we get a closed loop. You have to be able to draw current from somewhere. And then coming out of here, this is the signal current. Okay. So it looks a little bit like a diode, except you're going to see a lot more wires attached to it. Okay. As the name implies, it's an amplifier, so it amplifies a signal coming into the terminals, and the output is what comes from the signal current. So when we were talking about dependent currents and stuff before, a lot of times you could instantiate that using an op-amp. Okay. So let's talk about the operational principles of an op-amp. This is where it gets into ideal behavior. Okay. So I'm going to redraw my op-amp here. We're just going to kind of simplify it a little tiny bit. We're going to say that we've got a node here, and the voltage at that node is V+, and there's a current here that we will call I+. We're going to do the same thing down here. This is going to be V-, and the current going in there is I-. Okay. So the first operational principle is that the resistance into the amplifier is equal to infinity. Now this is for an ideal op-amp. Of course we know this isn't actually true, but we approximate it this way. Okay. What this means is that when we're looking at the currents going into the terminals, I+ and I-, we can treat them like they're actually zero. Like I said, in reality, they're not going to be zero, but they're going to be very, very small. So we idealize it and we say, well, so this implies that I+ and I- are equal to 0. Okay? So we can use that when we're doing our analysis. The second operational principle is that our signal current can go up to infinity, and so what this means is we can have an infinite amplification of the input signal. Well, that means if we're looking at the input signal is due to the difference between I minus and I plus. Well, and that implies that the difference is actually between V plus and V minus. Okay, that means since we can have an infinite signal current, we want to make sure that the difference is as small as possible, because otherwise we will never have enough current to amplify this. So what we're going to assume is we're going to assume that the difference between the two is actually 0. Okay? Again, in reality, it's not 0. It's very, very small. But so what this means is that V plus has to be equal to V minus. Okay? So we're kind of idealizing this. In reality, it doesn't work exactly this way. There's differences and things like that. But for the analysis and the simplification, this is close enough for what we need to do. So I'm going to begin with one example. And it's basically, let's just look at an inverting amplifier and see how we apply these idealized rules. Excuse me. Okay, so we have our amplifier here. We're going to put our inverting terminal there and non-inverting terminal here, and we're going to ground the non-inverting terminal. Okay, we're going to have our signal return also grounded, and then we're going to do a little bit of weird stuff here. We're going to have a resistor coming from a voltage source over here. We'll call that voltage source Vs, and then we're going to have a resistor going over from the inverting terminal, and it's going to connect up with our signal current, and we're going to say that this is at a voltage V out. So we want to know what this voltage V out is. Okay, this resistor is R1 and this resistor is R2. Okay, so for one thing, I want you to just notice that you can switch the inverting or non-inverting terminals when you're doing the schematic or the design. It doesn't necessarily have to be that way when you're doing when you're actually using an op amp, and some of you use them for your projects, then you actually have to be very careful about which pins you're using. But for the schematic, we can swap them around. That's fine. Okay, so that's the first thing. Terminals can be swapped in the schematic. Okay. Now second, we know that V plus has to be equal to V minus, right? So V plus, and this is going to be V minus, we know that our non-inverting terminal is grounded, and that implies that V plus has to be equal to 0, and that means that V minus also must be 0. Okay? So that's what that's the first thing you look at as far as what are your terminal voltages. If you can figure out one straightforward, then the other one has to be the same. Sometimes you have to do a little bit of math to figure it out. Okay, so let's look at, because we now know a couple of these voltages, we can write an equation for the node at the inverting terminal. And that will give us a relationship between our source voltage and our output voltage. Okay, so we're going to use a node voltage analysis, and I'm going to basically start with the branch going from the non-inverting terminal to the ground through the voltage source, right? Oops, sorry. Okay, so we know that V minus has to be equal to 0. Well, and that's going to be equal to Vs minus 0 over R1 plus the other branch, which is going to be V out minus V naught, which is 0, over R2. Okay. So if we're looking for V out, well, we can kind of simplify this a little further. We're just basically going to do some cross multiplication here and rearrange things. So we're going to have Vs over R1, and we're going to take that over to the left side, so that's going to become negative, is equal to V out over R2. Okay, that means V out over Vs has to be equal to minus the ratio of R2 over R1. Okay, so what this tells us is that the amplification is the ratio between the output and the input voltages. So this is our amplification. We want to know how much that voltage source is being amplified by the op amp, and that it's basically determined on the ratio between our two resistors. Okay, so for example, if we set R2 equal to 4 ohms and R1 equal to 2 ohms, then that means our amplification is going to be equal to minus 2. Okay, so if our voltage source is equal to 1 volt, then that implies our output voltage from the op amp is going to be equal to minus 2 volts. So it inverted it, which is why, I mentioned at the beginning that it was an inverting amplifier. It's negative rather than positive, and it's twice as large as when it started. Okay. Another example is a different circuit. Okay. This one is going to be a little bit more complicated to draw, so I'm going to start out here with, we're going to have our op amp down here. Okay. It's usually you don't have your signal return on the schematic, so you don't need to have that. I'm going to take this one off, but just know that it's always there, and if you don't see anything explicit, that means it's been grounded. Okay. So we're going to take and run this out here, and then we're going to have a resistor going here, and then another resistor down here, and this is going to be our ground. Okay, we're going to call this resistor R4, we're going to call this one R3, and then the voltage between that point and ground is going to be V2. Okay, then we're going to draw network up here, and the voltage between this point and ground is V1. This is R1. Okay, again, this is our V plus, this is going to be our V minus here, and we're going to take and run this over and connect it there, and this is R2. I think I have all my resistors on there. And then of course we've got our output voltage, right? So this is a different circuit, and I'll explain what we're doing in just a moment. Okay. So unlike the last one, we don't have a real clear picture of what the voltages are. So we just have to go with the fact that they're the same. And then we also remember that the currents I minus and I plus are going to be 0. Okay, so we're going to again start with our node voltage equations. So I will start with the inverting node, so up here, and I'm going to basically assume all of my currents are coming out. So I will start with V minus V1 over R1, so that is this path here, plus then we've got our second path, which is going to go up and around this way. And that's going to be V minus 2, our other voltage, which is going to be V out, or V not. We'll go with V out. R2. And then our third one is the current, but that just equals 0, so all this is 0, right? Okay. The second one is going to be from our non-inverting nodes, so I'm going to start with this path first. And so for that equation, I'm going to have V plus minus V2 over R3. And then we're going to take and follow this path here. And that's going to be V plus over R4. And that's going to be equal to 0 because, again, our current going into the amplifier is also 0. Okay, so they're both equal to 0, so I'm just going to set one equation equal to the other. V minus V1 over R1 plus V minus V0 over R2 is equal to V plus minus V2 over R3 plus V plus over R4. Now I'm going to make two simplifications. One is obvious based on what we've already talked about, and the second one is not quite as obvious. So first, I'm going to say that V minus and V plus are the same, so I'm going to replace V plus with V minus. Okay. Now the second thing is, and this one's not obvious, but it'll make sense why I did it later on, I'm going to set R4 equal to R2 and R3 equal to R1. So that means this is going to become R1 and this is going to become R2. And I'm going to rewrite the equation with those substitutions. V minus V1 over R1 plus V minus V naught, or V0 over R2 equals V minus V2 over R1 plus V minus over R2. Okay. Now, since I just have a single R1 and R2 in each of the denominators, I'm going to break up each of the equations and write them as separate terms for each of the expressions. So we'll have V minus over R1 minus V1. Oh, I wrote V. That should have been, sorry. That should have been minus over R1 plus V minus over R2 minus V0 over R2. That's equal to V minus over R1 minus V2 over R1 plus V minus over R2. Okay, so the first thing I'll notice is we've got a couple of terms that are the same on both sides. So this is going to go away because those are the same terms. And then this term will also go away. So we're only left with three expressions. Minus V1 over R1, minus V0 over R2, and that has to be equal to minus V2 over R1. I'm just going to get rid of all my minus signs by multiplying everything by minus 1. And then I'm going to solve for my output voltage. Okay, so V0 is going to be equal to, I'm going to have V2 over R1 minus V1 over R1, which I can simplify as 1 over R1, V2 minus V1. Okay, and then I multiply both sides by R2, so I now have R2 over R1 times V minus V2 minus V1. Okay, so what this is telling us is this is going to be the difference in the two voltages. Okay, that's why this is called the difference circuit. We can use this to kind of calculate the difference between two voltages. Okay, and this is going to be our amplification ratio. amplification ratio. So that means that what we choose for R2 and R1, and obviously that implies R3 and R4, will tell us how much the difference in those signals will be amplified coming out of there.